Pick out the true statement. Every group of order 36 is abelian. For this problem, we consider Z36. This group is cyclic and cyclicity implies abelian or commutativity. Cyclic implies abelian. So Z36 is abelian. But if we consider D18, order of D18 is 36. Means D18 group has order 36 and this is not abelian. So not abelian means not cyclic or implies not cyclic. Not cyclic. This is coming from negation of the statement because cyclicity implies commutativity. So not commutative implies not cycle, not cyclic. So this is the negation of the statement. Option A becomes wrong because for D18 group is not abelian but Z36 is abelian. But statement saying every group of order 36. That's why statement becomes wrong. Now come to option C. Every group of order 36 is non-abelian. So if group order can be written as P square, order of G can be written as P square where P is necessarily a prime number. Then group is abelian. But 36 order group you can write as 6 square and 6 is not a prime number. So already I gave you an example Z36 and D18. One is abelian and one is not abelian. So this statement is again wrong because of non-abelian. Now come to this statement B. A group in which every element is of order at most 2 is abelian. If we consider trivial group, it means only a single element containing. So trivial group always normal, always cyclic, always abelian. Sometimes you can say very simple. Simple means that there is no proper normal subgroup. So it is also simple. So trivial group or trivial set is always satisfy most of the algebraic properties. And you can say option B seems true. I am not saying in general, but seems true because we have an example supporting this statement. So you can say K4 whenever you are dealing MCQ based problem, always remember some example related to the problem so that you can easily discard the given options. So K4 other than identity element means non-identity element is of order 2, or you can say in other words non-identity elements of K4 is self-inverse element. So either you can say self-inverse or order 2, both are same. And in K4 non-identity, so if element A is non-identity, then order of A square, order of A is 2. This is true when A is coming from K4. K4 is Klein 4 group. Now this is the second example supporting statement B. So statement B seems true, but I am giving you general proof. So let's say element is of order 2. So if A and B two are elements of the group, then AB is the element by closure property. And suppose this is of order 2. So I can write like this. So you can consider this is a element. So post multiply by inverse. So what we have, and in left hand side. Now inverse come in reverse order. This is very known fact known as Soxu's property. So B inverse A inverse, and this is AB. So A and B both are self inverse, so we can write in place of B inverse B and in place of A inverse A. So finally we have AB equals to BA. This is the general rule to prove commutative property of the group. So if all non-identity elements are of order 2, then group is abelian. Or self-inverse element, identity element is also self-inverse. If a set containing all elements are self-inverse, then group is abelian. Option B is right.